Hello! What a lovely day it is today, my group, and I will talk about our final year project, which is biodiesel-ethanol blending as alternative future fuel. These are my group members: Vanessa, me myself Chung Kayu, Stephanie Blola, and Rowena Ng. For our project, we use biodiesel and ethanol as the blending fuel. Why we choose biodiesel and ethanol is because they are reduced pollutant, renewable, eco-friendly, sustainable energy source, and also reduce greenhouse gas emission. By blending these two materials, we hope to create an alternative future fuel. For our problem statement, we choose to blend biodiesel and ethanol together because ethanol alone still lacking on the physical properties compared to petroleum, and we also want to have a better understanding of this biodiesel-ethanol blending behavior for automobile application. The objective of our project is to develop biodiesel-ethanol blending with different composition as future fuel and to study the physical and chemical properties of biodiesel-ethanol blending as well as combustion performance. Our teamwork assignation is to prepare biodiesel-ethanol blends including pure biodiesel and ethanol. For individual assignation, each of us have one part, one person for combustion testing, and the other three each take density and viscosity testing, cloud and pour point observation, and Fdir analysis. Unfortunately, we did not include density in this presentation as the result is not as what we expected, so we just further discussed in the report. Significance of study. From this study, the aim is the establishment of biodiesel-ethanol blended as renewable alternative fuel and economical energy source for new option fuel generation in Malaysia. Next, I will pass to Rowena Ng.
Hi, I'm Rowena, and I will share about the difference between biodiesel, diesel, and ethanol. First is diesel. The essential condition for viscosity of diesel fuel normally detailed at 40 degrees Celsius. The major hindrance of diesel fuel is that it can turn into gel under cold weather due to increasing of viscosity as the temperature decreases, which may cause the fuel unable to flow smoothly in the fuel system. In diesel engine category, it has a main drawback involving the release of undesired particles in the long-running engine. Secondly is biodiesel. Biodiesel can be blended with petroleum diesel and used in standard diesel engines without engine modification. When biodiesel is run inside a diesel engine, the gases released reduce about 20% of carbon oxide, 40% of particulate matter, 30% of hydrocarbon, and 50% of smoke compared to diesel fuel. Biodiesel has greater lubricity property compared to diesel fuel, mainly low sulfur diesel fuel. And lastly is ethanol. Ethanol has a benefit of higher octane rating, more oxygen content, and lower carbon-hydrocarbon ratio compared to diesel fuel. Ethanol also contains higher vaporization heat, which frees the air initiated into the cylinder and thus reduce the end cylinder temperature. The cooling outcome of ethanol will boost the volumetric efficiency of the engine, and better brake thermal efficiency is granted. I'm going to pass the next slide to the next presenter.
Hi, thank you Rowena. My name is Stephanie Blola for methodology part. Firstly is prepare pure biodiesel B100 and prepare ethanol E100 and the ratio blends by volume B95, E5, B90, E10, B85, E15, B80, E20, B70, E30, B60, E40 and B50, E50. The second one is combustion test. Each blends including pure biodiesel and ethanol were prepared in 3 ml and combusted in empty can. Combustion appearance were observed and recorded over time. The third one is Fdir. After blending, each sample characteristic was tested and observed on Fdir, range between 4,000 until 1,000. The fourth one is cloud and pour point. The blends pure biodiesel and pure ethanol was left to under low temperature, and the result will obtained when they reach both cloud and pour point over time. The last one is viscosity. Viscometer model NDJ1 was used to obtain the viscosity of the blends B100, B80, E20, B50, E50, and E100. That is all for methodology part. I will pass it to Rowena Ng.
I will discuss about combustion of flame appearance and soot forming over time taken for each sample fully burned. According to the result, it is shown that E95 E5 has the largest flame appearance, meanwhile E100 has the shortest and smallest flame as compared to B100. Addition of 5 ml of ethanol in biodiesel bring oxygen into the fuel lead to enhance combustion. B80, E20 and B50, E50 both have moderate flame formation respectively. E100 has the smallest flame due to ethanol characteristic, which is easily evaporated. For soot forming, B100 produced the most soot compared to ethanol and others blend, meanwhile combustion of E100 produced zero residue on the ceramic plate. Amount of soot forming for B95, E5, B80, E20 and B50, E50 are little. These results indicate that pure biodiesel burns incompletely. Combustion of pure biodiesel will produce carbon dioxide, water, carbon, and carbon monoxide. Meanwhile, ethanol burns completely. The combustion of ethanol produces carbon dioxide and water. By adding ethanol into biodiesel fuel, it can reduce the soot formation, which leads to more cleaner burning. Due to ethanol can burn well because it is an oxygenate. B100 took the shortest time to fully burn, followed by B80, E20, E100, B50, E50, and B95, E5. Let us proceed to the next slide.
So we move on to the cloud point and pour point discussion. As you can see in the slide, the cloud point for B100 is 15.5 degrees, for B95E5 blending is 18 degrees, for B80E20 blending is 15 degrees, and B50E50 blending is 11 degrees. And for pour point, B100 is 11 degrees, B95E5 is 13.5 degrees, B80E20 is 12.5 degrees, and B50E50 is 9 degrees. So from the graph, we can see that B95E5 is higher temperature in both CP point. Based on the result that we obtained, can conclude that is almost same with the ASTM standard. On the right hand side, we can see the experiment pictures. Next, we will continue with viscosity discussion.
Thank you, Chungkayo. Next, I will proceed with viscosity. The viscosity for pure biodiesel in first, second, and third reading stays between 66 and 68 MPa per second. Next, for pure ethanol, it maintained approximately 63 MPa per second in the first and second reading, but fell to 42 MPa per second in third reading. For E20, the first and second reading are both 5 MPa per second and decreased to 3 MPa per second in third reading. For B50E50, all three readings are classed where the first reading is 23, second reading is 25, and 17 for the third reading. From the graph, we can see that B80E20 has the lowest viscosity. For B95E5, we didn't conduct the test as we assume that it has the same element as B80E20 based the Fdir analysis. Next, I will pass it to Vanessa Sharon. Bye!
Thank you, Stephanie. Hello, my name is Vanessa Sharon. So, the last one is Fdir analysis. From the analysis, the biodiesel and the blend shows that they have the same elements as when you saw it. In figure 1, all the results are stacked together in order to see how the reading is when they overlay. From figure 2, the biodiesel reading at around 3000 to 2800 has two peaks, which is aldehyde CH single bond. That is the dominant one compared with the one at the peak around 1750, which is ester C double bond or C. For B50E50, 3000 to 1500 is refers to vanished as it shows the same structure as the B100. After we add ethanol, it is found that there is additional weak broad peak at around 3500 to 3250 that refers to ethanol. For B80E20, it actually not much different from B95E5. At around 1500, it may be C double bond C. The peak at around 1750 is O double bond O. And the two peaks at around 3000 and 2800 is CH single bond. Lastly, for ethanol, it can be seen that at around 3500 and 3000, the peak OH is broad and strong. The alcohol is high, but when it is combined with biodiesel, it may be overlaid to the right side and the peak is much higher because the content of biodiesel has many CH single bond. We move on. Next, for recommendations, we recommend that the blends are tested inside a combustion engine like 4-stroke single cylinder and diesel engine. By conducting the test in the combustion engine, we get to see the engine performance much better like brake power, brake thermal efficiency, volumetric efficiency, fuel consumption and emission for nitrogen oxide, carbon dioxide and etc. And for the second recommendation is by using Redwood viscometer in order to know the fuel's viscosity. The viscometer MDJ1 that we use is not a standard viscometer. In the tests that were conducted, there may be human error when taking the reading. So, by using the standard viscometer that were made specially for determining the viscosities of petroleum oils, we can get the standard reading according to ASTM standard. In general, we cannot really develop the best biodiesel-ethanol blending ratio as future fuel as we are lacking in some equipment that we need. However, we are able to study the physical and chemical properties of biodiesel-ethanol blending as well as the combustion performance. Next slide. We expected our project cost is 2 ringgit and 26 cents in total. However, our actual project cost is only 2 ringgit. This is because the biodiesel is obtained from Sarawak oil pump in Tulu, while ethanol is from PKS laboratory. We only bought cubic ice. As for the additive, it is actually the ethanol that we use to blend with biodiesel. Actually, for commercial, biodiesel is much cheaper than diesel, where biodiesel only costs around 2 ringgit and 28 cents per liter, but diesel costs around 2 ringgit and 80 cents per liter. According to Advancing Convenience and Fuel Retailing, diesel fuel is more expensive. Diesel fuel is assessed a higher federal excise tax than gasoline, which is 24.4 cents per gallon for diesel versus 18.4 cents per gallon for gasoline. And diesel fuel is also sometimes assessed a higher tax at the state level. Finally, that is all from us. Thank you for lending your ears.